Okay, the answer to the questions in the previous slides is the low alloy steels. These steels, these alloy steels have been developed, okay, in order to overcome the deficiencies of plain carbon steel. And the cost for making these alloy steels will be higher than the plain carbon steel, due to the addition of alloying element. Okay, the principal alloying elements added to make alloy steels are manganese, nickel, chromium, molybdenum in the range of 1 to 4%. This table shows the list of the alloying element which can be added to the plain carbon steel. And you can see here, this column is about the classification or the designation of the low alloy steels. Classification. And this classification is depends on the types of the alloying element. Okay, we have here for the manganese, the steel number is start with 13XX, okay, and then for molybdenum, okay, 40XX, okay, and others, for nickel, okay, the classification or the designation is 81B XX. Okay, so this is how they classify the low alloy steels. It's referring to the types of the alloying element. Okay, this table is about the mechanical properties of low alloy steels. You can see here, this is the tensile strength, the yield strength, percent of elongation. Okay, and here you can see the IC SAE number for the low alloy steels. Okay, for the manganese steel, for this manganese steel, it consists of high percent of manganese, okay, and the number is 1340. Okay, and then we have here the chromium steels. Why it is called as a chromium steels? Because chromium is the principal alloying element. Okay, and then here we have the chromium molybdenum steels. Chromium molybdenum steels, and also the nickel steels. Nickel steel, molybdenum steels. Okay, so this name of the steel is based on the principal alloying element, which have been added to the low alloy steels. Okay. Okay, now we move to the another type of ferrous alloys, which is still under the steel group. Okay, now let's look at the stainless steel. Okay, the excellent corrosion resistance in stainless steel is due to the high percentage of chromium. At least 12% of chromium has been added yeah, in order to develop the stainless steel. Okay, chromium forming a thin film of chromium oxide, Cr2O3, on the steel surface. Yeah? And this chromium oxide layer, yeah, is actually protects the steel from further oxidation, making it stainless. Okay, here we can see an illustration. Okay, this is stainless steel, yeah, which consists of iron, carbon, and chromium. Yeah, at least 12% of chromium. Okay, and for this first picture is without any contamination. And then when this stainless steel part is exposed to the ambient air, okay, the stainless steel surface will be react with the oxygen in the ambient air. Okay, and then this reaction will produce a very thin protection layer, which is the chromium oxide layer. Okay, so this is the layer which protect the stainless steel. Okay, this is stainless steel. This layer will protect the stainless steel from corrosion. Okay, so here you can see the products of stainless steel, stainless steel structure, and stainless steel pot. Yeah? And you can also differentiate the appearance of the stainless steel based on the shining surfaces of the stainless steel compared to other types of metal. Okay, there are three main types of stainless steel. The first one is martensitic stainless steel. Okay, and the second one is austenitic stainless steel, and the third one is the ferritic stainless steel. Here, you can see the comparison between these three main types of stainless steel. But the first comparison is on the major alloy addition. Okay, for the metacitic stainless steel, the alloy consists of iron, chromium, and carbon. The percent of chromium is 12 to 70%. Okay? And for the austenite, the major alloy addition is chromium. Okay, where you can see here the percent of chromium is 16 to 25%. And on the same time, this austenitic stainless steel also consists of nickel, nickel alloy element. And for the ferritic stainless steel, the major alloy addition is chromium in the range of 12 to 30% chromium, which is higher compared to stainless steel, metacitic stainless steel, and austenitic stainless steel. Okay, for the metacitic stainless steel, martensite is the prime constituent. For the austenite phase, gamma, extended to room temperature, as the austenite is the micro constituent. Okay, and for the ferritic, alpha ferrite phase is the micro constituent. Okay, for the martensitic, this stainless steel can be heat treated For the austenitic, cannot be heat treated. For the ferritic, it also cannot be heat treated. Okay, for this martensitic stainless steel, high hardness in a steel tempered at high temperature, caused by the precipitation of alloy carbides. Okay, for the austenitic stainless steel, this austenitic stainless steel can be hardened and strengthened through cold working process. Because this austenitic stainless steel cannot be heat treated. So we can only use a cold working process. And same with the ferritic, because it cannot be heat treated. So it can be hardened and strengthened using cold working process. Okay. For the martensitic, it has the properties of magnetic, austenitic, not magnetic, ferritic, magnetic. Martensitic stainless steel is poor in corrosion resistance, while austenitic stainless steel better corrosion resistant compared to the martensitic due to the high chromium content. Okay, chromium is 16 until 25%, but for this martensitic, has a low corrosion resistance because of low percent of chromium. Okay, the strongest and hardest martensitic stainless steels can be achieved at high percent of carbon content. Okay, and this martensitic stainless steel used as machine parts and bolts because the properties is very hard, high hardness. Okay, and for this austenitic, it can be produced in largest quantities. For this ferritic, it can be used in high temperature application. Low cost and suitable to be used as construction materials. Okay, here you can see the microstructure for the three types of stainless steel. This is martensitic, where you can see the structure of needle-like structure of martensite. Okay, and this is the austenitic microstructure, where you can see the austenite phase microstructure, and this is the microstructure for ferritic stainless steel, which showing the alpha perite phase. Okay. Okay. Now we move to the cast iron. Okay. Cast iron is the big group of ferrous alloys. In ferrous alloys, we have the steels and also cast iron. Okay, what is cast iron? Cast iron is the alloys which can be cast into desired shape instead of being cold worked in the solid state. Okay, it contains 2 to 4.5% carbon and 1 to 3% silicon. Okay, if you look at here, this is the iron carbide. This is iron carbide diagram. Carbide phase diagram. The same diagram as before, but for this diagram it stops until 6.70, which is this phase diagram stop at the cementite phase. Okay. For the cast iron, the composition of carbon is from 2 until 4.5. But in practice, most of the cast irons contains between 3 to 4.5% carbon. Okay, still in the range of the general properties for cast iron. Okay, alloys within this composition range becomes completely liquid at the temperatures between 1150 and 1300 degrees C, which is lower than the steels. So meaning that for the cast iron, this cast iron has a low melting temperature compared to the steel. Okay, let's look at here. If you compare, this is for steel, less than 2 is steel, and please remember some of the knowledge from the previous chapter. Okay, this is liquid phase, and this line is the liquidus line. Liquidus line. This liquidus line, is separate, between these two phases, between the liquid and also liquid plus gamma phase. And any point on this line will represent the melting temperature of the alloy. Okay, so you can see here less than 2, okay, less than 2, okay. So this area having higher melting point compared to the cast iron, which having more than 2% of carbon. So this is area of steel, where you can see the melting temperature is higher than the cast iron. So this is the cast iron region. This is steel region. You can see the melting temperature for the steel is higher compared to the melting temperature for cast iron. Okay. This cast iron, because of that, this cast iron are easily melted and amenable to casting. Okay. This cast iron is very brittle. Okay. Because of this cast iron is very brittle, it cannot be deformed using the mechanical work process, mechanical deformation process. So the most suitable process in order to fabricate the product using this cast iron is by using a casting process. Okay, comparatively low cost with versatile engineering properties. Okay, cementite. You can see here, this is cementite. It's metastable compound. So this cementite is easily to decompose to alpha ferrite plus graphite. Okay, so this is the reaction. Okay. Okay, this is the true equilibrium iron-carbon phase diagram. True equilibrium iron-carbon phase diagram. This figure, okay, iron, carbon phase diagram, extends to 100% carbon. It extends to the 100% of carbon. if you compare with the phase diagram in the previous slides, yeah, the phase diagram in the previous slides stopped, yeah, until 6.67 weight%, yeah, which is under cementite phase. Okay, such that graphite is the carbon-rich phase, yeah, instead of cementite at 6.70 weight% carbon. Yeah. So for this true equilibrium iron-carbon phase diagram, yeah, graphite, yeah, is the carbon-rich. Yeah. Graphite is the carbon-rich phase, meaning that, yeah, graphite is the phase which having high or rich, yeah, percent of carbon. Okay, graphite formation is promoted by two factors. One is the composition of the silicon. Okay, and the second one is the cooling rate. Yeah, slower cooling rates during the solidification favor graphitization. Yeah, which is the formation of graphite. Yeah, at slow cooling rates. Okay, there are four main types of cast iron. Yeah, we have here white cast iron, grey cast iron, malleable cast iron, and ductile cast iron. Okay, now let's look at in details, yeah, about this type of cast iron. Okay, first look at the grey cast iron. Okay, this grey cast iron consists of 2.5 to 4 weight% carbon and 1 to 3 weight% silicon, which promotes the formation of graphite. Okay, so that's why we're referring to the equilibrium phase diagram of the iron carbon. Yeah, you can see here the diagram N adds 100% of carbon. Yeah. Okay, and then carbon exceeds in the amount that can dissolve in austenite and precipitates as graphite in the form of flakes and surrounded by an alpha ferrite or pearlite matrix. Yeah. For this formation of alpha ferrite or pearlite matrix, yeah, it depends on it depends on the cooling rate. Okay. Why it is called as grey cast iron? Because the fracture surface of the graphite flakes appears grey. Yeah? Appears grey. That's why we call it as a grey cast iron. Yeah? So here you can see the microstructure of the grey cast iron. Yeah? You can see here the graphite is in the form of flakes. So this black flake structure, okay, is referring to, okay, this black flake structure is referring to the graphite flakes. Yeah? And this graphite flake is surrounded by this white region, yeah, which is called as a alpha ferrite matrix. Okay, and this is a 3D image, yeah, of the microstructure. Okay, you can see the clearly the shape of a graphite. Yeah, graphite. Okay, this grey cast iron is weak and brittle in tension due to the tips of the graphite flakes are sharp and pointed. So you can see here, this is a graphite flake, and it has a tips. End of the graphite flakes. All graphite flakes will have tips or sharp edges. And these tips may serve as points of stress concentration when an external tensile stress is applied. So that's why this grey cast iron is weak and brittle in tension. Okay, the strength and ductility, because the grey cast iron is very brittle, so the strength and the ductility of the grey cast iron are much higher under the compressive loads. Okay, and this grey cast iron is very effective in damping vibration energy, and it's widely used as a base structures for machineries and heavy equipment which exposed to vibration. High wear resistance and excellent machinability, and least expensive compared to other metallic materials. Okay, different microstructures of the grey cast iron can be generated by the adjustment of composition and cooling rate. Okay, when we reduce the composition of silicon and increase the cooling rate, it will prevent the complete dissociation of cementite to form graphite. So it will produce graphite flakes embedded in a pearlite matrix, like this. In the previous slide, I showed the microstructure of the ferritic grey cast iron, which can produce at a slow cooling rate. When we increase the cooling rate and also lower the silicon content, it will produce pearlitic grey cast iron. Pearlitic meaning that these graphite flakes, in both pictures you can see the graphite flakes, but for the pearlitic, these graphite flakes is surrounded by the pearl-like structure. While for this ferritic, this graphite flake is surrounded by the alpha ferrite structure. Next, we move to the ductile cast iron. Ductile cast iron, or we can also call this cast iron as nodular cast iron. How to produce this ductile cast iron? This ductile cast iron can be produced by adding a small amount of magnesium and cerium to the grey iron before casting. Will produce different microstructure and mechanical properties of material. So from this process, from the addition of the small amount of magnesium and cerium to the grey cast iron, it will produce ductile cast iron, which having different microstructure and mechanical properties. This ductile cast iron has 3 to 4% carbon, and 1.8 to 2.8% silicon and low impurities. Graphite still form in this cast iron type, but as nodules, or sphere-like particles instead of flakes in the grey cast iron. The matrix phase, if you look at the microstructure, the matrix phase can be pearlite or ferrite. It's surrounding the nodular particles. These nodular particles is the graphite. That's why this cast iron called as a nodular, because of the nodular shape or sphere-like shape of the graphite. Okay, this cast iron good fluidity, castability, machinability, and wear resistance. It has high strength, high toughness, and high ductility and hardenability due to the spherical nodules of the graphite. And this graphite phase, because of the nodular, the microstructure of the ductile cast iron, also called as a bullseye type microstructure. So this graphite looks like a bullseye type microstructure. Okay, next we move to the white cast iron. Okay, white cast iron. This cast iron has low carbon, 2.5 until 3%, and silicon, also low silicon, 0.5 to 1.5% silicon content. For low silicon cast iron and rapid cooling rates, most carbon exists as cementite instead of graphite. So that's why for this cast iron, we refer to the iron carbide phase diagram. We refer to this phase diagram, which this phase diagram is end at 6.70% of carbon. Okay. The fracture surface of this alloy appears white and crystalline. So that's why this cast iron is called as white cast iron. Okay, the light cementite region are surrounded by pearlite. Okay, you can see here the white region. This white region is pearlite. And this pearlite, this white region is surrounded by a pearlite structure. Pearlite structure is the alternating layers of ferrite and cementite. Of ferrite and cementite. Okay, so meaning that this structure consists of ferrite and Fe3C. This pearlite structure is an alternating layers. Okay, alternating layers of ferrite and cementite. Okay, due to the large amount of cementite, white iron is extremely hard, brittle, and excellent wear resistance. Okay, next we move to another type of cast iron, which is the malleable cast iron. It consists of 2 to 2.6% carbon and 1.1 to 1.6% silicon. How to produce this malleable cast iron? This malleable cast iron use the white cast iron as an intermediary in the production of the malleable iron. Okay, start with heating the white cast iron at the temperature between 800 to 900 degrees C for prolonged time. Causes a decomposition of the cementite and forming graphite, which exists in the form of clusters or rosettes. And this graphite is surrounded by ferrite or pearlite matrix depending on the cooling rate. Here you can see the rosettes or clusters is graphite structure surrounded by the alpha ferrite matrix. Okay, and it can also be surrounded by the pearlite matrix. Pearlite is alternating layers. And it depends on the cooling rate. Okay, the irregular nodules of graphite are formed in this process. Okay, when we heat the white iron for a prolonged time. Okay, this cast iron has good stability, machinability, moderate strength, toughness, and uniformity. Okay, in this slide, this slide has summarized to you the types of the 4 cast iron. We have the grey cast iron, and then we have the nodular cast iron. Then we have the white cast iron, white cast iron, and malleable cast iron. So from this slide, we can see how these 4 types of cast iron can be produced. Okay, it starts with the commercial cast iron range. So if you look at here, in order to produce a grey cast iron, okay, this is grey cast iron. If we if you apply slow cooling rate, it will produce ferritic grey cast iron, meaning that the graphite, okay, the black color is indicate the graphite, is surrounded by the ferrite. And if we do moderate cooling, it will still also produce grey cast iron, but this time the graphite is surrounded by the pearlitic structure, the alternating layers. Okay, and then when we do fast cooling, on the cast iron, it will produce a white cast iron. Okay, you can see white cast iron consists of pearlite and cementite. Okay, this P is referring to the pearlite. Let me write down here. P is pearlite. GF is graphite flakes. And then GN is graphite nodular. And GR is graphite rosettes or cluster. Okay, fast cooling, it will produce graphite, white cast iron. And then when we reheat this white cast iron, at the temperature of 700 degrees C for a prolonged time, for example 30 hours, when we do slow cooling, it will produce ferritic malleable. When we do fast cooling, it will produce pearlitic malleable. Yeah? What is the difference? The difference is the difference is for the slow cooling, it will produce a microstructure, yeah, which having a graphite rosette. Okay, the black area, the black region is referring to the graphite rosette, surrounded by the ferritic phase. Yeah? While for this one, when we do fast cooling, yeah, on the white cast iron, yeah, it will produce graphite rosettes or clusters surrounded by the pearl-like structure, pearl-like layers, and it's called as a pearlitic malleable. So this is how the production of cast iron. Yeah? This is how to produce the 4 types of cast iron. Okay, what is the limitation of ferrous alloys? Yeah? Ferrous alloys are high density. High density. Ferrous alloys are low electrical conductivities and poor corrosion resistance. Okay, the main disadvantage of the ferrous alloy is this material is susceptible to corrosion. And here you can see some of the products, yeah, has been corroded when exposed to the ambient temperature or corrosive environment. Okay. Okay, now let's move to the non-ferrous alloys. One of the example of non-ferrous alloys is aluminum and its alloys. Yeah? Pure aluminum is very light, easy to cut, low strength, high ductility, and less expensive, so that it is suitable to be used as a material for making drink can. Okay, in order to improve the properties of the pure aluminum, we have the aluminum and its alloys. Aluminum and its alloys have been developed, in order to improve their pure aluminum properties. Okay, aluminum and its alloys, having high strength, low density, compact to steel. The density for aluminum alloys is 2.7 gram per centimeter cube, while steel is having 7.9 gram per centimeter cube. And for this alloy, aluminum alloy, having high electrical and thermal conductivities, and also high resistant to corrosion. Okay, in terms of the advantage, this alloy is ductile even at a very low temperature. For the disadvantage, this alloy having low melting temperature, at the temperature of 660 degrees C, which restrict the maximum temperature at which it can be used. And this alloy is suitable to be used for making the materials for the transport body panels, surgical equipment, and also for making windows frame. Okay, this table is about the types of aluminiums. according to the composition. Okay, and then you can also see the properties of the various types of aluminium in this table and also the application. Aluminium and its alloys is divided into rough and cast aluminium alloys. Okay, for the rough aluminium alloys, this is the number, this is the association number of the types for rough alloys. While this one is the number for the cast aluminium alloys. And these numbers, depending on the composition of the alloys. Okay. Now let's move to the another types of non-ferrous alloys, which is on the copper and its alloys. Pure copper is a reddish brown, malleable, and having excellent conductor for heat and electricity, so that it is suitable to be used as an electrical fitting and wires. Okay, there are few types of copper alloys. Bronze. Bronze is a copper alloy having the alloying elements of tin and phosphorus. Okay, while brass is a copper alloy having the zinc as the alloying element. Besides that, another type of copper alloy is copper nickel alloy. And this type of alloy is suitable to be used for making pins, nuts, screw, and decorative artifacts. Okay, this table shows the mechanical properties of various types of copper alloys. Okay, you can see the tensile properties, yield, and also the ductility. Among these various types of the copper alloys, beryllium, which is the most common heat-treatable alloys, has the highest tensile strength compared to others copper alloys. Okay, highest tensile strength. And then excellent corrosion resistance and also excellent wear resistance. Next, we move to magnesium and its alloys. Pure magnesium is very light and having low Young's modulus. Okay, that's why scientists develop magnesium alloy in order to improve the pure magnesium. For the magnesium alloy, the alloying elements are aluminium, zinc, and thallium. Okay, which is rare earth metals to produce alloys with high strength to weight ratios. Okay, alloys with lowest specific gravity, which is lightweight, high strength, good high temperature mechanical properties, and also corrosion resistant. These magnesium and its alloys have been used widely for making the component for automotive, component for a motor car. Okay, here you can see some of the component in cars made of magnesium and its alloys. Okay. Okay, for the magnesium and its alloy, it also can be divided into rough and cast alloys. Here you can see the number, the ASTM number and the UNS number, based on the composition of the magnesium alloys. Okay, here you can see the tensile properties, yield strength properties, and also the ductility. Okay, we have reached to the end of the part 1 for chapter 8. Thank you for listening, and see you again in the part 2 of chapter 8.